is at the beginning, I'll do a of what we've gone over, and then I'll do the sample exam. Okay, so the distance between 2 points in the plane with coordinates x1, y1, x2, y2 is just the square root. Well, the distance is the square root of the sum of the difference of the square of the difference of their coordinates. And so d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Well, if I do this in 3 space, where of course now this is has an extra coordinate here, then the square of the distance is just x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And so a sphere centered at HKL of radius r satisfies the equation x minus h squared plus y minus k squared plus z minus l squared equals r squared. The norm of a vector. Suppose I have a vector v with coordinates, with components v1 comma v2. Then the norm of v is the square root of v1 squared plus v2 squared. If I have a vector v with components v1 comma v2 comma v3, then the norm of v is equal to the square root of v1 squared plus v2 squared plus v3 squared. The field properties. So this is, I think, a 7-tuple, 2, 4, 6, 7, yes. So a field is a 7-tuple where, well, we have some set f, and in the following, let me suppose that A is an F, B is an F, and C is an F. Along with, the set F, we have the binary operators addition, going from the Cartesian product of the set F with itself into the set F. And we have multiplication, the binary operation multiplication, which maps the Cartesian product of the set F with itself into the set F. We have the new unary operators, negation, the additive inverse, which takes members of the set F and maps into members of the set F. We have, again, a multiplicative inverse, which is a unary operator mapping members of the set F into members of set F. We have the nullary operators, the zero, the additive unit, the additive identity, which takes, well, nothing and maps into the reals, into the set F. We have 1, the multiplicative identity, which maps, well, nothing into the set F, meaning that these are members of the set F. So we have the field properties are, well, the closure property of addition, A plus B. If A is an F and B is an F, then A plus B is also an F. The closure property for multiplication. If A and B are an F, then A times B is an F. The associative property of addition. A plus B plus C is the same as A plus B plus C. The associative property of multiplication. A times B times C is the same as A times B times C. The commutative property of addition. A plus B is the same as B plus A. The commutative property of multiplication. A times B is the same as B times A. The existence of additive identity. We have a nullary operator there exists 0 in the set F, such that for any A in the set F, A plus the additive identity is equal to A. And so I have that 0 is a right additive identity by the commutative property of addition. I also have that 0 plus A is also equal to A. Therefore, it's both a right and left additive identity. It is the additive identity. We have the existence of a multiplicative identity. We have the nullary operator, which gives us the member 1, the multiplicative identity, which is a member of the set F. So that's that for every member of the set F, in every member A of the set F. A times the multiplicative identity is just equal to A by the commutative property of and so we have that this is a right multiplicative identity by the commutative property of multiplication. We also have that 1 times A is equal to A, so it's both a left and a right multiplicative identity. It is the multiplicative identity. So I also assume that we have non-trivial fields. Again, this is this is assumed for courses in analysis, but not for courses in algebra. We have that I assume that the additive identity is different than the multiplicative identity. This is just so that we don't happen to have the possibility of only having a field consisting of one number. The existence of the additive inverse. So we have a unary operator such that for every member of the set F, there exists, well, the additive inverse of that number A, of that member of the set F, A, and it is such that A plus the additive inverse of A gives me the additive identity. And so this is a right additive inverse. Similarly, we have by the commutative property of addition that minus A plus A is 0. So it's both a left and right additive inverse. It is the additive inverse. We have the existence of a multiplicative inverse. So for every non-zero element in your set F, there is a multiplicative inverse of that element such that A times the multiplicative inverse of A gives me the multiplicative identity. And so this is a right multiplicative inverse. By the commutative property of multiplication, we also have that the reciprocal of A times A is 1. Therefore, this is both a right and left multiplicative inverse, so it's a multiplicative inverse. Lastly, we have the distributive property that multiplication distributes over addition. So A times B plus C is A times B plus A times C. Okay, so these give you the field properties. I put a square over everything so that you'll note the difference between, well, members of your scalar field and your vector space. And so let me give you your vector space properties. And so a vector space is a 12 tuple. It is, in addition to the field, the 7 tuple of a field, we have an additional 5 tuple. And so the vector space is this 5 tuple over my 7 tuple, the field. Again, let me assume that in the following, so I'd have to keep rewriting this, that U, V, and W are in your set V, and that C and D are in your set F. I put little arrows to denote the fact that I'm in my set V, and I put little squares to denote that I'm in my set F, the field. Just like the operators in the set in the field have squares. Oh, and well, I guess, and the operators in my vector space, I guess where the arrows over, I put little circles, made circles around them. But if they're members of the set V, I put little arrows over them. Okay, so we have these. So in addition to, we've already gone over the field. We have these binary I have a binary operator of vector addition, which takes the Cartesian product of the set V with itself into the set V, and we have scalar multiplication, which is the Cartesian product of the set F with the set V, and it maps into the set V. We have the unary operator of vector additive inverse, which takes members of the set V and maps it into members of the set V. And we have a nullier operator, the zero vector, which takes nothing and it's mapped into the set V. So these satisfy the following. The closure property for vector addition, if U and V are members of the set V, then U plus V is also a member of the set V. The commutative property for vector addition, U plus V is equal to V plus U. The associative property for vector addition, U plus V plus W is the same as U plus V plus W. The existence of the identity for vector addition. And so there's a nullary operator, 0, in the set V, such that for any vector U, any member of the set V, U plus 0 plus the additive identity is equal to U. And so I have that 0 here is a right additive identity. By the commutative property for vector addition, I have that 0 plus V is also equal to V. So it's both a left and right additive identity. It is the additive identity. The existence of an inverse for vector addition. There is this unary operator that maps V into itself, which is such that for any U, there exists minus U, such that U plus minus U is equal to the additive identity. And so negative U is just a right additive inverse. But by the commutative property for addition, we have that minus U plus U is also equal to 0. So it's both a left and right additive inverse. So it's additive inverse. We have the closure property for scalar multiplication, that if I take any scalar, any member of the set F, and I multiply it, scalar multiply it by a member of the set V, then a scalar multiplying a vector is a vector. Scalar multiplication distributes over vector addition. So I have that if I take a scalar C and I perform scalar multiplication on the sum of the vectors u and v, then this is equal to the scalar multiplication of C and U plus the scalar multiplication of C and V. Notice that now you can tell when things are scalars and when I'm adding vectors. Scalar multiplication distributes over the addition of scalars. And so C plus D times U is just CU plus DU. The associative property for scalar multiplication. C times D times U is just C times DU. The equality of the scalar identity and the scalar multiplicative identity. 1 times U is just equal to U. Okay, so that gives me the definition of a vector space. A unit vector in the same direction as V is defined as, well, a new vector U, which is just the vector V divided by the norm of the vector V, the dot product. Suppose A is a vector with components components A1, A2, A3, and B is a vector with components B1, B2, B3. Then A dot B is A1, B1 plus A2, B2 plus A3, B3. Of course, etc. for vectors of other dimensions. The properties of inner product. Let A, B, and C be vectors, and let D be a scalar. Then A dot A is always greater than or equal to 0, and A dot A is equal to 0 if and only if A is equal to 0. Again, this is actually not necessary. You can prove this from these, but I include it because most people include that in the properties of the inner product. Next, A dot B is equal to the complex conjugate of B dot A. A plus B dot C is just A dot C plus B dot C. And D A dot B is just equal to D times A dot B. You can always bring scalars out in front of your dot product. A vector space with an inner product is called the inner product space. If every series of vectors which converge absolutely imply that the sequence of vectors converge, then we say that this inner product space is called a Hilbert space. I should say sequence. Okay. Properties of the dot product. We have that the square of the norm of the vector A is just A dot A. 0 dot any vector A is 0. A dot B is the same as the norm of A times norm of B times cosine theta. Therefore, if A and B are not the 0 vectors, then cosine of theta is just A dot B over norm A, norm B. The vectors A and B are orthogonal if A dot B is equal to 0. We define the direction cosines of some vector A, some non-zero vector A, as well the components of the unit vector. And so let A over the norm of A be the vector with components cosine alpha, comma, cosine beta, comma, cosine gamma. And so the direction angles, alpha, beta, and gamma, satisfy. Again, I'm assuming I'm not divided by 0. So let me assume that this is not the 0 vector. A is not the 0 vector. Then cosine of alpha is A1 over the norm of A. Cosine beta is A2 over the norm of A. And cosine gamma is A3 over the norm of A. The scalar projection. And so the scalar projection of the vector B onto the vector A, the component of B onto A, is A dot B over the norm of A. The vector projection of the vector B onto the vector A, again, assume that A is non-zero, is A dot B over A dot A times A. The orthogonal projection of the vector B onto the non-zero vector A is B minus the vector projection of B onto A. The distance from the point P1 with coordinates x1, x2 to the line written in standard form, ax plus by plus c equaling 0 is equal to the absolute value of ax1 plus by1 plus c over the square root of a squared plus b squared. Next, the CBS theorem. And so the CBS theorem, the Cauchy-Brunakowski-Schwarz inequality, says that the absolute value of A dot B is less than or equal to the norm of A times the norm of B. The parallelogram law says that the square of the norm of A plus B plus the square of the norm of A minus B is twice the square of the norm of A plus twice the square of the norm of B. Cross product. Let A be a vector with components A1, comma, A2, comma, A3, B be a vector with components B1, comma, B2, comma, B3. Then A cross B is defined to be the vector with components A2, B3 minus A3, B2, comma, A3, B1 minus A1, B3, comma, A1, B2 minus A2, B1. So we have the following properties of the cross product. That A cross B is orthogonal to both A and B. That the norm of A cross B is the norm of A times the norm of B that times sine theta, where I assume that theta is between 0 and pi. If A and B are non-zero, then A and B are parallel to each other if and only if the cross product is equal to 0. A cross B is equal to minus B cross A. And the scalar D times A cross B is the same as D times A cross B. So you can take scalars out in front. The cross product, A cross D times B is the same as D times A cross B. Again, you can take scalars out in front of your cross product. The cross product distributes over addition. A cross B plus C is A cross B plus A cross C. We have that, that scalar multiplication, that the dot product and the cross product associate with each other, more or less, whatever, or analogous to being associated. being associative. So A dot B cross C is equal to A cross B dot C. There's a relationship between the cross product and the dot product. A cross B cross C is A dot C times B minus A dot B times C. If A is a vector with components A1, comma A2, comma A3, sorry, B is a vector with components B1, comma B2, comma B3. C is a vector with components C1, comma C2, comma C3. Then A dot B cross C is the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3, the triple product. The area of the parallelogram is determined by the vectors A and B. It's just the norm of A cross B. The area of the triangle determined by the vectors A and B is just 1/2 the norm of A cross B. The volume of the parallelepiped is determined by the vectors A, B, and C is just the absolute value of the triple product, A dot B cross C. The torque is defined as the radius cross product with the force. Vector equation through R0 in the direction of V. It's just R is equal to R0 plus TV. The parametric equation of the line through the point with coordinates x0, comma y0, comma z0 in the direction of the vector with components a1, comma a2, comma a, comma b, comma c is x equals a0 plus x equal x0 plus at, y equals y0 plus bt, z equals z0 plus ct. The symmetric equation through the point with coordinates x0, comma y0, comma z0 in the direction of the vector with components a, comma b, comma c is x minus x0 over a equals y minus y0 over b equals z minus z0 over c. The 2-point form through the points with coordinates x0, comma y0, comma z0, and the point with coordinates x1, comma y1, comma z1 is x minus x0 over x1 minus x0 equals y minus y0 over y1 minus y0, z minus z equals z minus z0 over z1 minus z0. The parametric equation from the vector r1 to the position vector r0 to the position vector r1 is r of t is equal to 1 minus t r0 plus t r1. The vector equation of the plane through the position vector r0 with normal n is n dot r minus r0 equaling 0 and n dot r equaling n dot r0. The scale equation of the plane through the point with coordinates x0, comma y0, comma z0 with normal being the vector with components a, comma b, comma c is a times the quantity x minus x0 plus b times the quantity y minus y0 plus c times the quantity z minus 0 equals 0. The linear equation of the plane ax plus by plus cz plus d equals 0. The distance d from the point with coordinates x1, comma y1, comma z1 to the plane written in standard form ax plus by plus cz plus d equaling 0 is the distance is the absolute value of ax1 plus by1 plus c z1 plus d over the square root of a squared plus b squared plus c squared. A surface consisting of all rulings parallel to a given line passing through a given plane curve is called a cylinder. If A, B, C, D, E, F, G, H, I, J are members of your field, then then the solutions to the equation ax cubed plus b x squared y plus c x y squared plus d y cubed plus e x squared plus f x y plus g y squared plus h x plus I y plus j equaling 0, a general cubic equation in R2. It's called an elliptic curve. Again, we can simplify it so it can be written in the form x cubed plus ay squared equaling x cubed plus bx squared plus cxy plus dx plus e. A quadratic surface. Let A, B, C, D, E, F, G, H, I, J be members of your field, your scalar field. Then a solution to this quadratic equation in 3 variables. A x squared plus b xy plus c xz plus dy squared plus e yz plus fz squared plus gx plus hy plus I z plus j equaling 0. It's called the quadratic surface. We can, again, simplify it so it looks to be one of 2 forms. Ax squared plus by squared plus cz squared plus d equals 0, or in the form ax squared plus by squared plus cz equaling 0. Now, of course, it could be that of course, we mean that one of them, that 2 of them are squares and one of them is linear. Not necessarily only the z one. And so the standard form for these the equations of these quadratic surfaces are, well, ellipsoid. So if I have x squared over a squared plus y squared over b squared plus z squared over c squared equals 1, then this is ellipsoid. It's an egg. And this actually doesn't look like a bad drawing. I must actually spent a while on this guy. And so this is A. Well, let's assume that A is positive. So this is A, this is B, and there we go. Let's assume that each of these are non-negative. So this is distance A, distance B, distance C along the X, Y, and Z axes. If A, B, and C are equal to each other, then this is a sphere. We have a hyperboloid of 1 sheet. This one isn't drawn that great, but the other 2 aren't bad. Okay, so I have here x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Something like this. X squared over a squared minus y squared over b squared minus z squared over c squared equals 1. It's something like this. So notice oddball, so it goes along the x-axis. Oddball, so it goes along the y-axis. And minus x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Again, it doesn't look as good, but I tried as best I could. And so the oddball is the x, so it opens up along this x-axis. Okay, and notice that there's 1 oddball, so it's 1 sheet. Okay, hyperboloid of 2 sheets. And so, again, it opens up in this case, or whatever, along the z. So I have x squared, and there's 2 negatives, so it has 2 sheets. Minus x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. Minus x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. It will look like this. So now it goes along the y-axis. x squared over a squared minus y squared over b squared minus z squared over c squared equals 1. So now it goes along the x-axis. Okay. I guess my y's and z's I can do, my x's I don't do as well. Okay, yeah, x's just don't do as well. A cone. So if I have z squared over c squared equals x squared over a squared plus y squared over b squared, it looks like this. Y squared over b squared equaling x squared over a squared plus y squared over c squared. It opens in the, so this opens in the z, this in the y direction. This will be in the x direction. X squared over a squared plus y squared over b squared plus z squared over c squared. Elliptic paraboloid. So again, this will open up in the z, x, y direction. And so I have z over c equaling x squared over a squared plus y squared over b squared, something like this. Y over b equaling x squared over a squared plus z squared over c squared, something like this. X over a equaling y squared over b squared plus z squared over c squared. It looks something like this. Hyperbolic paraboloid. If I have, oh, I guess I only did one. I guess I was lazy. I only did one of them. I only did one. Obviously, in the other direction, I probably couldn't draw the other ones. So I could probably draw the other ones. I could only draw this guy. Okay, so z over c equaling x squared over a squared minus y squared over b squared. Looks something like this. Limit. Suppose r goes from the reals into 3 space. So r is a maps r into R3. Suppose it's a vector with components f of x, g of x, comma h of x. Then the limit as t approaches a of r of t is the vector with components. Limit as t approaches a f of t, comma, a limit as t approaches a g of t, comma, limit as t approaches a h of t. I have that r is continuous at a if the limit as t approaches a of r of t is equal to r of a. The space curve C is a set of all triples, ordered triples, all 3 tuples, x, comma, y, comma, z, such that for every I in the every t in the interval I, x is equal to f of t, y is equal to g of t, z is equal to h of t, where f, g, and h are continuous functions on the interval I. A knot is an embedding of the circle S1 into R3. We have all of these properties of the derivative, the usual sort of properties of the derivative. I define r prime at t to equal the limit as h approaches 0 of r of t plus h minus r of t over h. And so this is the same, this is equivalent to saying that r is differentiable if the limit as h approaches 0 of r of t plus h minus r of t minus r prime of t times h over h is equal to 0. If r is a vector with components f, comma, g, comma, t, then r prime is a vector with components f prime, comma, g prime, comma, h prime. I have the sum rule. The derivative of u plus v is the derivative of u plus the derivative of v. The constant multiple rule. The derivative of a constant times u is the constant times derivative of u. Therefore, we have that the derivative is a linear transformation. So we have the linearity property. The derivative of au plus bv is A times the derivative of U plus B times the derivative of V. We have the product rule. A scalar function f times u, the derivative of a scalar function f times u is just the derivative of f times u plus f times the derivative of u. We have the derivative of the dot product. U dot v is just u prime dot v plus u dot v prime. We have the derivative of the cross product of u and v is just the derivative of u cross v plus u cross the derivative of v. And we have the chain rule. U, the derivative of u composed with f is just the derivative of u composed with f times the derivative of f. Well, the definite integral follows the same sort of idea. Let R be a vector with components f, g, and h. Then the integral of R is the vector with components integral from a to b of f, comma, the integral from a to b of g, comma, the integral from a to b of h. We have the arc length. S is the integral of the norm of R prime. And so S prime is just the norm of R prime. We have the formulas for the curvature. The curvature of is equal to the norm of the second derivative of R with respect to the arc length S. It is the norm of the derivative of the unit tangent vector as a function of S. It is the norm of T prime over the norm of R prime when it's a function of some parameter T. It is the norm of R prime cross R double prime over the cube of the norm of R prime. That's when you, when you write it component-wise, you'll use that formula. If instead you write it as in functional notation, suppose you have the curve y equal f of x, then the curvature is the absolute value of the second derivative of f divided by 1 plus the derivative of f squared, all to the power of 3/2. We have the unit tangent vector is just r prime divided by the norm of r prime. We have the principal unit normal vector, which is r double prime divided by kappa, assuming that these are all functions of the arc length. It is t prime divided by the norm of t prime, assuming that these are all functions of some parameter t. The binomial vector is just the unit tangent vector, Cartesian cross product times the principal normal vector, unit normal vector. My normal plane is the plane which contains the vectors n and b. The oscillating plane is the plane that contains the vectors n and t. The rectifying plane is a plane that contains the vectors t and b. My torsion was defined, my torsion tau is defined by the following equation, that the derivative of the binormal is equal to minus tau times the normal, assuming everything here is a function of arc length. The radius of curvature is just 1 over the curvature. The oscillating circle is a circle which is in the oscillating plane through some point P having radius the same as the radius curvature. the Frenet-Serre formulas say that, well, T prime is kappa n prime is minus kappa T plus tau B, and B prime is minus tau n. Let R be the position vector. Then the velocity vector V is just R prime. The speed, unfortunately, is denoted also by S, is the norm of the velocity vector. The acceleration vector, A, is the derivative of the velocity vector. It is the second derivative of the position vector. Newton's second law of motion says that F is equal to ma. We have the equations for projectile motion. That x is equal to v0 cosine alpha t. So assume I have some initial velocity, with magnitude v0 and some angle of elevation that we launch this projectile. And the only force is the force of gravity pointing down. Then x is equal to v0 cosine alpha t, and y is equal to v0 sine alpha t minus 1/2 gt squared. We have the tangential and normal components of acceleration, that a is equal to a sub t times t plus a sub n times n, where a sub t is the derivative of your speed, and a sub n is your curvature times the square of the speed. Okay, so that was a quick. Okay, so let's do the following. So what I did yesterday is I went through and I did a preview for the exam. So I wrote down the problems from the preview. So let's do that. So problem 1, compute. So these are possible questions from your exam. So if I would have taken the exam yesterday, then these are the questions that would have been given to me on the exam. Again, your exam is, everyone is going to have a slightly different version of the exam, but they're going to be similar type problems. So these are similar problems to, what you would get when you actually take the exam. Okay, so problem 1, compute the vector projection of V, a vector with components 3, 2, 6, onto the vector U, a vector with components 9, 6, 6, into the sum of the coordinates of this projection rounded 4 decimal places. Okay, so let's do that. So first off, let me write the formula for the vector projection. And so my vector projection, the projection of the vector V onto the vector U is V dot V over U dot U times U. Okay, so let's do that. So this is equal to, well, maybe I'll do it in 2 steps. I'll do V dot V. And so that's just going to be 3 squared plus 2 squared plus 6 squared. Okay, so let me do that. And so this is,
what do you want?
36 plus 4 is 49.
Look at my back. Look at my back. Look at it.
And so U dot U.
Look what you did. Did you see that?
Is equal to 9 squared plus 6 squared plus 6 squared, which is 81 plus 72 is 153. Okay. And so
Okay, tell
the
us
projection.
the last ones. Call them over here and see
And
as well
it's
who's still
actually, I
here
think
and
I
come
might
here.
have one more page. So the projection of the vector v, sorry, of the projector v onto the projector u
Says he's never here.
is therefore 49 over 153 times u, which is 966. Okay, and that is my vector projection.
Can you say the question again?
Right. So I haven't answered though. I haven't put the number in yet to actually whatchamacallit, to actually, enter into the computer. Can you scroll down?
Hey, what time is it?
10:07. And so let's find the sum of the coordinates. Then I'll actually plug it into the calculator. So the sum of the coordinates are going to be, well, I won't use a notation, will equal, so the sum will equal whatever this number is, 49 over 153. Nine plus 6, 21. And now let me plug that into my calculator. Okay, so do that.
Who's this first? Is this yours?
And it's
Can you add? Could you just add something? Are these yours?
No. And so this will be 49 times times 21 divided by 153. Oh, well, maybe I'll just write that. Do 43 over 51, which is approximately 6.725 4901.961. So we would plug into, it's 4 decimal places. And that's the number that you would input into your computer, where it says, there's a little answer box. So in the answer box, you would plug that number. Any questions about this? Okay, so let me do problem number 2. So problem number 2 says, find the scalar and vector projection of B onto A. Determine the exact value of both the scalar and vector projection. Enter the scalar projection rounded 4 decimal places. Okay, so let's do that, where A is the vector with components 1, 0, 2, and B is the vector with components 2, 7, 3. Okay, so let's do the scalar projection first. And so the scalar projection vector B onto the vector A. So that's just the scalar part. So it's A dot B over A. Okay, so let's try to figure that out. So first, I guess, let me try to figure out A dot B. Okay, so I have here A. So it would be a 1, 2 plus 0, 7 plus 2, 3.
Do you want them to do adult ours?
And so I get here 8.
Did you hear what I asked?
Let me look at the square of the norm of A. And so that's 1 squared plus 0 squared plus 2 squared,
I want to
which
go to
is
sleep.
5. So therefore, the norm of A
Okay.
is rad 5.
Okay. Could you come over
And
here
so
and go
the
to sleep,
scalar projection
please?
is 8 over rad 5. I have to add, because I still need the vector projection. And so this is approximately divided by 5, 8 divided by square root 5 is.
Wait a minute. You have to, if you're going to tell me, I'll do it for you. You have to
5,
see what you're doing.
7,
What do you
7,
want?
7,
Huh?
0, 8, 7, 6, 4. Okay, so we have that scalar projection. This is approximately 3.5, 4 decimal places, 7, 8.
I'm trying.
Oh, wait,
I'm trying. Very good.
4, that's 7, 7. I'm wrong. So that's what you would enter into your text box. Now let's figure out the vector projection. Well, the vector projection of the vector B onto vector A is just the scalar projection,
Okay.
because we've already figured that out.
Okay. Okay.
Times A over the norm of A.
Okay. Ready?
Okay, so the vector projection of B onto A is 8 over rad 5.
Oh my God.
Times.
I told somebody not to take these. And what did they do?
Well,
took
we're
them.
dividing by the norm of A, which is rad 5, and then multiplying by the vector A, which was 1, 0, 2. And so I get 8/5. So I'm going to multiply each of these by 8/5. My vector projection. Any questions about that?
Please listen to me. Do you want me to help them or no?
So
What?
one second. Okay, so problem number 3. Find the work in joules by a force F in newtons, a vector with components 1.4, 5.5, 8.3 that moves an object from a point with coordinates -0.1, -8.8, 2 to the point 4 points with coordinates 4.6, -4.1, -1.0 along a straight line. The distance is measured in meters and the force in newtons. Into the work in joules rounded to 4 decimal places. Okay, so let's do that. So my work is just the force dot the distance. Okay, so let's figure out the distance. So I'm going to have to subtract each of these. So I'm going to have to subtract. And so I have 4.7, 4.7. Okay, so that's a 4.7. This is also 4.7, and that's a -12. Okay. And so let's figure out the work. Well, it should be the absolute value of this. And so negative. Seems like I'm going to get. Okay, so I have here the work. So let's just multiply by the force. And this is going to be in newtons. Okay, so let's do that. So 1.4, 5.5, 8.3. So it's 1.4. Okay. I guess I'm going to have to do that on a calculator. Okay, so that's what? Okay. There. Okay, so 1.4, 4.7, 5.5, 4.7, 12, 67.17. This will be in joules. They want it anyway. So any questions about that? Okay. Let me do problem number 4. A quarterback throws a football with an angle of elevation of 84 feet and a speed of 61 feet per second Find the horizontal and vertical components of the velocity vector. Calculate the exact value of each of these components and write this calculation on your answer sheet. Enter the vertical component in feet per second, rounded 4 decimal places in your answer box. Okay, so let's do this. I'm going to draw a triangle. So this is 61 feet per second. This is 84 degrees. Therefore, this component is 61. Well, maybe I'll call it the horizontal component is 61 cosine 84 degrees feet per second. And the vertical component I guess I have to have a V here. Okay. So the vertical component of the velocity vector is 61 sine 84 degrees feet per second. So these are their answers. And what do you want? You want the vertical. Okay, so the vertical, which is the 61 sine 84 degrees, is approximately, put that in, and I'm sure this only gives you degrees. Yeah, it only gives me degrees. Okay. So this is 61 sine 84. It's almost, oh, because he's almost throwing it straight up. That's why. This is almost, he's almost completely straight up. So this is 60.665835 6175 feet per second. So what you would enter into your text box would be this answer. Any questions about that? Okay. Next. A block and tackle pulley suspended in the warehouse by ropes of length 3.4 meters for the rope on the left and 2.0 meters for the rope on the right. Hoist weighs 1,676.8 newtons. The ropes fastened at different heights make angles with a horizontal 64 degrees for the angle on the left and 50 degrees for the angle on the right. Find the tension in each rope and the magnitude of each tension. Calculate the exact value for each of these and write this calculation on your answer sheet. Enter the magnitude of the tension for the rope on the left in newtons, rounded 4 decimal places in the answer box. Okay, so let's draw this. So I have some big thing here, and this guy has weight, or maybe I shouldn't draw that yet. So this has a weight of 1,167 at 1676.8 meters. Okay, and this is 3.4 meters. And 2 is the other side. So this is 3.4 meters. Oops. Don't get that close. This is 3.4 meters. And the other one is 2 meters. Okay.
Okay. Now, where
Oh,
does,
and the angles
where-
are
I'm asking you a question.
64.50. So 64 degrees and 50 degrees. So again,
Oh my God.
let this be the I direction
Should I be looking for these kids or not?
and the J direction. Yeah, so I'll upload this to along with the video. So I'll upload the video and the PDF to Canvas, basically in the same location as the other sample exams. I'll just attach it to the sample exam sort of thing. Okay. So now let's call this T2. I don't really care. T1, T2 is being the length.
Did you understand?
If this is 64, this is also 64 degrees. And this is also 50 degrees. So this is the length of this will be T2 cosine 64 degrees. Length of this is T2 sine 64 degrees. Length of this is T1 cosine 50 degrees. Length of this is T1 sine 50 degrees. Okay, so, and maybe I'll call this T3. It's not really attention, but okay, so I have here T1 plus T2 plus T3 is 0. I'm assuming statics, meaning that I don't want this object to move around at all. And so I don't want this to move. So I assume that all the forces cancel out. So I have here T1 is equal to, well, let's see, that's in that component. I'm doing it in the minus one first. So it'll be a minus T1 cosine 50 degrees I plus T1 sine 50 degrees J. And for T2, it's T2 and maybe let's orientate it this way so I don't have to
Do you
look at that. So it's T2
Oh, could we talk for 1 minute?
cosine 64 degrees. That's in the positive I direction. And T2 sine 64 degrees. And that's in the positive J direction. And then T3 is that's in the negative J direction. Negative 1676.8 in the negative J direction. Okay, good. So now this equation here will imply, well, the following. Okay. And let's look at the I components. So I have I don't know, maybe so I have a negative T1 cosine 50 degrees plus T2 cosine 64 degrees I. And notice that the J component, so plus T1 sine 50 degrees plus T2 sine 64
Okay.
degrees minus 1676.8 degrees for J is 0. So that implies my first equation. So I must have that each of these are equal to 0. So I have minus T1 cosine 50 degrees plus T2 sine 64 degrees is equal to 0. And for R2, again, let's bring the 1676.8 to the side of my equation. Why does it look like it has a degree symbol? And so I have T1 sine 50 degrees plus T2 sine. That's a typo.
Okay.
They were both cosines. Okay, so these are both sines. 54 degrees equals 1676.8. Okay, so now let me send you another. There's one more page here. So I have that if I multiply the first equation by sine 50 degrees,
Oh my God. Will you stop for just 1 second?
if I multiply the second equation by cosine 50 degrees, I get, well, these will cancel. And so this is going to be T2 times. I can factor out my T2 because that's in common. That's going to be a cosine.
Do you still want me to watch what they're wearing?
64 degrees.
Huh?
1 second. Okay. And so it is, I multiply by sine. Well, maybe actually I'll write it here. So it is T2. I'm going to factor that out. So that's cosine of 64 degrees, sine 50 degrees, plus sine 64 degrees times the cosine of 50 degrees is equal to, well, 0. So that's okay. Plus I multiply the second equation by the cosine of 50 degrees. So let's recall the following. Recall. Again, you could rederive this just using Euler's formula. You can rederive all these sum formulas in different formulas, and I did that in class. And so the sine of alpha plus beta is sine alpha cosine beta plus cosine alpha. Oh, okay, plus cosine alpha sine beta. Well, I guess I wrote it in the opposite, order, but it's still the same thing. So from here, I get that T2. So this becomes the sum of those 114 sine of 114 is equal to 1676.8 cosine 50 degrees. Therefore, T2 is equal to 1676.8 cosine 50 degrees over the sine of 114 degrees. So that's one of my magnitudes. Okay, so now I need at least probably 2 more pages actually. Okay, so now I have here R1. I have this equation here. So I have from R1.
What are you gonna do? What are you gonna do today?
Let's bring the T1 cosine 50 degrees on the side of my equation. I have that T1 cosine 50 degrees is equal to T2 cosine 64 degrees.
Do you want the names on there now or no? Do they know them or no?
And so, well, we know what T2 is. So I have that T2 is equal to 16, maybe I'll skip one more one. T1 is equal to T2, which is 1676.8 cosine 50 degrees over sine 114 degrees times cosine 64 degrees. So that's this. Let's divide by the cosine of 50 degrees to solve for T1. But then the cosine 50 degrees cancel.
Where do you leave it when I'm looking for you?
So therefore T1 is equal to 1676.8 cosine 64 degrees over the sine of 114 degrees. And there's the other magnitude. Now let's try to find the actual tensions. Okay, so let's find the tensions of these. So I have that, well, from
what? From what?
this equation. Oops. From this equation here. We have T1 let me factor out a magnitude, the T1 without the vector. So this is T1 minus cosine 50 degrees I plus sine 50 degrees J. And now let's just plug in. And so let me plug in T1. And so I have the tension T1 is equal to 1676.8 cosine 64 degrees over sine 114 degrees times minus cosine 50 degrees I.
Do you want us just to hear what they're going to for, or do you want me to go low? I can't stand here all day.
And that is my tension. Next, I guess we need one more page. I was almost done, but not quite. Next, well, we also have the other tension. So this is copy. I also have this tension here. And so I have that T2. Let me factor out the T2s here that are in common. It's equal to T2 cosine 64 degrees I plus sine 64 degrees J. And let's just plug in the, oops. The magnitude T2, which was the same as that, but it's cosine 50. Okay, so it's 1676.8 cosine 50 degrees over the sine of 114 degrees times cosine 64 degrees I.
Okay, so you need this
plus
anymore,
sine
right?
64 degrees
Is it?
J.
Huh?
And that is the other tension. And lastly, they asked me something. So they asked me left, right, left. So they're asking me T1. Okay, so they're asking me what is T1, which is cosine 64 degrees. So T1 is 1676.8 cosine 64 degrees over sine 114. So that was my T1.
What time is it?
10:45. So this is T1. Okay, so now let's plug that in. My calculator. And so 16, 7, 6.8 cosine 64 degrees divided by sine 114 degrees is 804.624 1517447, and I think everything was in newtons. And so let me round, I guess, to 4 decimal places. So if I round here to 4 decimal places, one, two, three, 4. And that is what I would enter into my text box. Any questions about that? Okay. Let me do problem number 6.
I did have a question.
Yes.
Was it asking for just the length of the row for T1? Or
Yeah, it's asking for the tension.
oh, the tension? Okay.
Yeah, meaning the magnitude. It's asking for the magnitude of the tension. So it's asking for the magnitude of the tension on the left, which I call T1. And so it's asking for the magnitude of tension on the left, and that's denoted by T1 in my case. We actually never used the lengths.
Okay. Yeah.
Okay. Any other questions about that? Okay. Again, basically, these are all sort of problems from physics. Well, most of these were problems from physics so far. Okay, problem 6. Determine the acute angle between the 2 lines. Calculate the exact value of this angle, acute angle. You write this calculation on your answer sheet. Enter the acute angle in degrees, rounded to 4 decimal places in the answer box. So -99 x plus 30y equals -5. 100x plus 80y equals -52. Okay, so let's do this. So first off, I have my first equation. I don't know, let's call it R1 or something, or L1. Is -99 x plus 100, no, 30, plus 30y equals -5. And so I have that 30y, sorry, is equal to 99x minus 5 divided by 30. Oh, that's going to be 3.3. Six. Okay, I can do it that way. Okay, so the slope of my line is 3.3. In decimals rather than fractions, because it turns out to be a nice sort of decimal. And so that a vector in this direction, change in y over the change in x. And so a vector in the same direction as this line is this vector. So I pick this as being a vector in the same direction as this. You know, you can pick other things, but this is at least one vector in the same direction. Let's do L2. And it won't matter, you know, as long as I have a vector in the same direction as this line. Let's look at the second line and do the same thing. So it's 180, 52. Okay. So again, I want to find the slope of this. Probably 2 pages. Okay, so I have that 80y is equal to -100x minus 52. And so y is equal to -100 over 80 minus 52 over 80. So that's going to be divided by 5/4. Um, 26, 13/20. It doesn't really matter. Hopefully, actually, I'm doing this. I should actually do these on calculators. Not that I don't trust myself, but why don't I actually do it on calculator? 99 divided by 30. Three. 100 divided by 80. Fraction. That's what. 1.25. Okay, correct. I knew it was correct, but I still wanted to check. Of course, the other one's 0.65. But I don't care. Okay, so I have here that the slope is negative 1.25. I don't care. Therefore, my other vector, that's a change in y. Okay, so again, I could put the negative on the other one. I don't know, maybe I'll write it that way. So this is a vector in the direction as the second line. Okay, so now let's try to find the angle between these. And so let's find the formula for the dot product. Or the angle, well, whatever it is. The angle formula for the dot product. So we have here A dot B is the norm of A times the norm of B times cosine theta. And we'll try to make theta be between 0 and pi. Okay, so let's figure out A dot B. -1 plus 3.3 times 1.25. So let me do that. Certainly too lazy to do it. That's an easy calculation. 3.3 times 1.25 minus 1 is the norm of A squared is 1 squared plus 3.3 squared. 1 and 3.3, yes. And so I get
So I'm going, okay.
11.89. And so the norm of A is the square root of 11.89. That looks like the norm of B,
Water.
and then 1 squared plus 1.25. Is 1.25 squared is 5.625. Okay. So I have here A dot B is equal to norm of A and so I have cosine theta equals 3.125 divided by the square root of, let's multiply those together. Point 468.125. And that's an exact value. Okay. So now theta is equal to arc cosine of 3.125 over the square root of 30.468.125. And that's your answer. And they wanted the approximate answer. Okay, so let's do that. Like this. So it's the arc cosine of 3.125 divided by the square root of 30.468.125 is 55. 5182070218, which is to 4 decimal places, 55.5182 degrees. So that's what you would enter into your text box. Wait, 55? Yeah, 55 degrees. Okay. Any questions about that? Okay. Let's do problem number 7. A force with magnitude 20 newtons acts directly upward from the XY plane on an object with mass 4 kilograms. The object starts at the origin with initial velocity of v0 equaling I minus j. Find its position function and its speed at time t. Enter the sum of the components of the position rounded 4 decimal places when t is equal to 18.5. Okay, so let me do that. Okay, so first off, we have here that force is equal to 20 newtons, and it's going straight up. And so it's in the, wait. Sorry. So it's directly up in the K direction. We have that by Newton's law.
This is killing me. Like devils do. I can't get it any better.
Force equals mass times acceleration. And the mass was 5. No, the mass was 4. The mass was 4 kilograms. So the mass was 4. So I have that the acceleration is 5k. Okay, so let's integrate. So let me get probably 2 more pages. So I have that the derivative of the velocity is equal to integral of 5k t. Okay, so if I integrate, again, the derivative of the velocity, so I'm just integrating both sides of my equation. Again, the derivative of velocity is acceleration. Okay, so I have that the velocity is equal to 5t plus some constant c. Well, the initial velocity is I minus j. It's I minus j. So I plug in t equals 0. Therefore, my constant vector is just I minus j. Okay, so my velocity is I minus j plus 5t. Okay. So let's integrate that. And so let's integrate the velocity, which is the derivative of the position vector. I j 5tk.
What time is it
11:05.
right now?
And so I have that the position vector
Okay, call
is equal to
call my brother.
ti minus tj
Mhm,
plus 5 halves
mhm.
t squared k plus some constant. I'm assuming that I'm starting at the origin. Oh, there it is right there. I'm assuming that I'm starting at the origin.
Uh-huh.
And so 0 is equal to 0i
Okay.
minus 0j
Okay.
plus 5 halves 0k.
Mhm.
Oops. Plus c. So it implies that c is just 0. And so my position function is t minus tj plus 5/2 t squared k. And that is my position function. Okay, next. Find its position. Oh, find its position and its speed. Well, we already figured out its speed. I just didn't write it. I didn't know that. And, oh, speed. I'm sorry. It says speed, not velocity. And its speed. Okay, let's figure out the speed.
Why don't we just do it? Oh my
Okay, and so, ooh, how's that already out? And so
God. Okay.
it was, where is it? Here it is. Here's
Okay,
the velocity.
Call Joey, my brother.
So let's do the speed.
He might not be good.
And so it is 1 squared plus -1 squared plus 5t squared. And so this is equal to 25
Okay.
t squared plus 2.
Okay.
So therefore, the speed is radical
Okay.
25 t squared
Got it,
plus
dog?
2. And lastly, we want to find the position, right? No, some of the components of the position, yet the position at 18.5. Okay, so let's find the sum of the components. Let's add one last, oops, one last page here. And so components, here they are. It is,
Mhm.
so the sum of the components is t minus t plus 5/2 t squared. And so the sum of the components is 5/2 t squared. And so I want to figure out the sum of the components. At, I think 18.5 or something, 18.5. And so the sum of the components is just 5 divided by 2 times 18.5 squared.
Mhm.
So let's see what that is.
Okay. Well,
855.
mhm.
0.625. I forgot my units. I think they're feet per second. Oh, I'm clicking on the wrong thing. Okay, trying to pull the wrong thing. These are not. These are in
Was it rain?
meters per second.
Was it rain?
These are in meters.
Was there rainer?
And so this is meters per second.
Yeah, it must have been half the bad shit.
And that's what you should type into your text. Okay, so let me do problem number 8. Find the length of the curve, determine the exact length, and into the approximate length around 4 decimal places. And so the position vector r is 3 cosine 20t I plus 3 sine t 20t j. Oops. plus 20 ln cosine 3tk for t between 0 and pi over 18. And so define the length. This is just the integral. I don't know, it's like from t0 to t1. Oh, integral from t0 to t1 of the norm of r prime. Okay. So let's figure out r prime. So derivative of sine of cosine is minus sine. So it's a minus 3 times the sine of 20t times 20. Oh, I guess I'm doing it in this notation. Not that it really matters. Derivative of, again, sine is cosine. So it's cosine of 20t times the derivative of what's inside, which is 20 times your 3 gives you 60. And then lastly, derivative of ln is 1 over cosine 20t times the derivative of what's inside, which is a minus sine. (20t) times derivative of what's in 3t. 3t times derivative of what's inside was 3 times your 20, which is 60. Okay. Which is just tangent. Okay. And so let's look at the norm of r squared, which is a negative 60 sine 20t squared plus 60 cosine 20t squared plus minus 60 sine over cosine is tangent squared, which is factor out my 60 squared from everything, which is 3,600, but maybe I'll leave it 60 squared, times what remains, which is sine squared, 20 degrees, 20t, plus cosine squared, 20t, plus tangent squared, 3t. Okay. Who knows? Okay, so this is sine squared 20t plus cosine squared 20t is 1. One plus tangent squared is secant squared. Therefore, the norm of r prime is 60 secant 3t. Okay, so that simplifies nicely. Okay, so now let's find the length. Integral from 0 to pi over 18. (60) secant 3t dt. The integral of secant is ln secant tangent and since I have a 3 out in front, 3 inside, I have to divide by 3 between 0 and pi over 18. Okay, so this is equal to 20 ln secant pi over 6 plus tangent pi over 6 minus 20 ln secant of 0 plus tangent of 0. Okay, so let's draw something. This is a 30, 60, 90 triangle. And so this implies that the arc length 20 ln of secant. And so that's 2 over rad 3. Tangent is 1 over rad 3. Secant of 0 is 1. Tangent of 0 is 0. Ln of 1 is 0. So that last term goes away. So this is 20 ln of 3 minus 20. I have here a negative, I have 3 to the negative a half that can factor out. And so that becomes a negative 10 ln 3. And so this simplifies to 10 ln 3. And it says to round, so this is the exact value. So it's 10 ln 3. And let's do 10 ln 3. 10.986 1228867. And I don't think there are any, I don't think there, I said any units here. It's just whatever's. Yeah, there are no units. And so S, the length is approximately 10.9861. And that's what you would enter into your answer box. Any questions about that? Okay. Oh, I could have also, again, just written it as, I guess I could have just simplified this as a square root of 3 and then gone directly to that. Or do it that way. Okay. Let me do problem number 9. Find the length of the curve, determine the exact length, and enter the approximate length rounded 4 decimal places. So r is equal to 6i plus 9t squared j plus 6t cubed k for t between 5 and 7. Let me do that. So again, the arc length So that's my arc length formula. Let's take your derivative. And again, I'll use this notation. So it is derivative of a constant is 0. Derivative of 9t squared is 18t. Derivative of 6t cubed is 18t squared. Okay, so let's find the norm. Square the norm. The 0 squared plus 18t squared plus 18t squared squared. So this is equal to factor out 18 squared. 18, well, maybe I'll write it this way first. Plus 18 squared to the 4th. Factor out 18 squared t squared. Okay, let's do that. Okay, so this is 18 squared t squared times 1 plus t squared. Okay. The norm of r prime is 18t radical 1 plus t squared. This is since t is between 5 and 7. T is positive. So I don't need any absolute values or anything. Okay, so that means that the arc length, the length of your curve is the integral from 5 to 7. I better be sure it's 5 to 7. Yes, it is 5 to 7 of 18t
Are you done?
radical 1 plus t squared dt. So let u equal 1 plus t squared. So du is 2t dt. So t dt is 1/2 du. So the arc length s, when t is 5, u is 26. 1 plus 5 squared is 26. And when t is 7, u is 50. 1 plus 49 is 50. 18 divided by 2 is 9 rad u. Okay. Guess I need another page. So the arc length is equal to u to the 3/2 times 2/3, which is 6. 9 times 2/3 is 6. So the arc length, so the length is 6 times 50, radical 50, since I have a power of 3 halves, minus 6 times 26 times rad 26. So 300. Oh, I can factor out a 5. Rad 2 minus 156 rad 26. And so the length is 1500 rad 2 minus 156 rad 26. And so you can plug that into your calculator. So let's do that.
I'm not sure, I don't know.
Oops. Minus 156 rad 26, which is 132587 3299 4392. And so 4 decimal places. Okay, it's 1325.8733. And that's what you would enter.
I'm dying. I'm dying. Is there anything else?
Any questions about that? Okay. Let me do problem number 10. Find the length of the curve rounded 4 decimal places. So R is the vector with components 3t squared, comma 27t, comma 12t to 3 halves. T is between 2 and 8. Okay, so again, the length.
Is there something we could drink before this? Because when I try it, nothing goes.
Integral
I'm
from
wasting
0
time.
to T1, the norm of R prime. So let's figure out R prime. I'll use this notation. Oh, it's already using it. So 6t 27, 3618, t to the 1 half. Okay. And so the norm squared is 6t squared plus 27 squared plus 18t to the 1 half squared. Let's factor out a 9. Okay, so that's going to be a 4t squared plus 81. Factor out a 9 from the 27 squared, and factoring out a 9 from the 18 is 36. Okay, so try it in a better order. So I have the norm R prime squared is 9 4t squared plus 36t plus 81 . Yes, it is. It's a perfect square trinomial. So this is a perfect square trinomial. Okay, good. So I have here 2t quantity squared is 4t squared. 2t times 9 times 2 is 36t, and 9 squared is 81. So therefore, this is 3tt plus 9. T is between 2 and 8. 2t plus 9 was never negative. So therefore, the length integral from 2 to 8 of 2t plus 9. So it's equal to 3t squared plus 9t, 2, 8. +64 plus 72, 4 plus 18. So that's 22, that's 50, 150, that's 114 times 3. Is 342. I guess it's both the end, so it's also rounded to 4 decimal places. Okay, so it's actually a very nice, a really nice number. So you would enter that also into your text box. Any questions about that? Okay. Let me do problem number 11. Find the unit tangent, the unit normal vectors t and n, and find the curvature. Enter the approximate value of the curvature around the 4 decimal places where t is equal to 4.7. And so r here is equal to t cubed j plus t squared k. Okay, so let's do this. So I want to figure out, well, unit tangent. Normal vectors and curvature. And I have r. And so the formulas are, maybe I'm not going to write it. I'll write them next to each other. And so this is equal to r prime over the norm of r prime the normal is equal to t over the norm of t prime, sorry, t prime over the norm of t prime. And the curvature is equal to the norm of t prime over the norm of r prime. Okay, good. So those are all the formulas that I'll be using to figure out each of these. Okay, so t cubed t squared. So it's just t cubed t squared.
Are you gonna just stay
So
there
R.
all day?
Prime is t cubed t squared. Okay, good. So that's
Think about P.
that's the derivative. Okay, so now let's find the norm of the derivative. The square of the norm of the derivative. So that's 9t to the 4 plus 4 t squared. So that's
How did you
t
get
squared,
these
9t
when you say
squared
you don't
plus
have any
4.
pills?
And again, t is, oh, so it doesn't say, but t's, I'm assuming here for t positive. Okay, so t positive. Well, we're only going to be evaluating the positive value of t. So I get rid of the, oops. Get rid of the absolute values here. Okay, so R is equal to t rad 9t squared plus 4. Okay, good. And so therefore, t is equal to R. So let's divide each of those. So let's divide those out. So 0, comma, 3t over rad 9t squared plus 4. And the t's cancel. And so 2 over rad 9t squared plus 4. Okay, so that's your unit tangent vector. Let me actually write this as 9t squared plus 4 to negative 1/2 times the vector 0, 3t, 2. Okay, so let's find the derivative of this. We use the product rule. And so I'll bring down the negative 1/2, subtract 1 from it, and then multiply by the derivative of what's inside, which is 18 t. And so this is minus 9t. Times the second plus the first times the derivative of the second. Derivative of 3t is 3, derivative of 2 is 0. And so I get here, let's factor out 9t squared plus 4 negative 3 halves. So what remains? Multiply negative 9t inside the parentheses, inside the vector. 0, negative 27t squared, negative 18t. Multiply the 9t squared plus 4 inside the parentheses. You get a 0. 9t squared, so it's a 27t squared plus 12 and a 0. Okay, so let's simplify this. So this is 9t squared plus 4 to the negative 3 halves times 0 plus 0 is 0. The 27t squares cancel. Minus 18t. Okay, good. Let's try to find the norm of this. And what happened to the vector symbol? Okay. Let's look at the norm of the squared. And so that just squares this. So this is 9t squared plus 4 and negative 3. And let's square each of these and add them up. Okay. So this is 9t squared plus 4, negative 3. Okay, so let's take a 6 squared out. Actually, maybe I'll put the 6 squared out front, which of course is 36, but times 9t squared plus 4, negative 3. So now let's see what remains here. So I factor out a 6, so that's a 4. I factor out a 6, so that's a 9t squared. Okay, so this becomes 6 squared over 9t squared plus 4 squared. Okay. And again, I'm assuming here t is greater than equal to 0. So I have that. I don't have to worry. Actually, it's squared. I don't have to worry about signs anyway. So this is 6 over 9t squared plus 4. Okay. So now let's try to find the unit normal. Okay. And so n is equal to t divided by this. So dividing by this term is the same as multiplying by its reciprocal. And so it is 9 t squared plus 4 over 6 times t prime. So there's t prime. Well, here's t prime, which is 9t squared plus 4 to the negative 3 halves 0, 12, 18. Okay, cancel out the sixes. Okay, so that's 1 over the square root, or maybe I'll leave it as 9t squared plus 4 to the negative 1/2 times the vector 0, 2, negative 3t. So maybe I'll leave the square root out. And the other one I left it in. So I'll leave this, I'll put the square root in. So I'll put the square root inside of it, because that's what I did for t. So for n, is 0, 2 over the square root of 9t squared plus 4, negative 3 over the square root of 9t squared plus 4. Okay. And there. And that's it. Okay, good. Lastly, let's find the curvature. Kappa. That's just going to be this, which is 6 over 9t squared plus 4. The norm of t prime. So that's a norm of t prime. And then the divided by the norm of r prime. Divided by, there it is. So now dividing by so I'll take the reciprocal of, so that's a t over the square root. Okay. T, 9t squared plus 4. Yes. I guess I just need one more page. So I have here with the curvature is 6t over 9t squared plus 4 to the 3/2. And that is my curvature. And then they wanted you at like 5.7 or something like that. Something. 4.7. So they wanted to figure this at 4.7. Okay, so let me plug that into my calculator. And so 6 times 4.7 divided by 9 times 4.7 squared plus 4 to the power 3/2. So it is 0.0097637143, 4 decimal places. So 0098. And that's what you should put into your answer box. Any questions about that? Any questions about that? Okay. Let me do problem number 12. Okay, so problem 12, find the curvature of R, the vector with components t, comma t squared, comma t cubed at the point 1, 1, 1. Determine the exact value of the curvature and enter the approximate value rounded 4 decimal places. Okay, so let's figure out the curvature. So I'm given this. So the curvature. So the formula I use for curvature is the norm of R cross R double prime over the norm of R prime cubed. Okay, so let's figure out R prime. Okay, so t squared, t cubed. T squared, t cubed. Okay, so now let's take the second derivative. Derivative of 1 is 0, derivative of 2t is 2, derivative of 3t squared is 6t. And now let's find the cross product. So it's 12t squared minus 6t squared is 6t squared. 12t squared minus 6t squared is 6t squared. 0 minus 6t is minus 6t. And then 2 minus 0 is 2. And so that is the cross product. Oh, actually, maybe you should actually write out more than this. I'm getting lazy and just sort of writing the answers out, but you should write down more of the steps because you probably can't do this all in your head. Okay, so sorry, I'm just getting lazy. Okay, so I have here the square of the norm of this cross product is 6t squared squared plus 2 squared. So that is 36 t to the 4 plus 36 t squared plus 4, 9t squared plus 9t plus 1, which I guess you can't factor. That's, you need a 6 in there. Okay, so the norm is equal to 2, rad 9t squared plus 9t plus 1. Okay, let's, oh, you know what? I only want to find the curvature at a point. Oh, I was stupid. I only wanted to find it at a point. You know that? I only wanted to find it at when t is 1. Okay, so wait 1 second. So I actually only want to find this, which will simplify my life a lot. So this is just 6 minus 6/2. So now let's find out the norm of this. So I have 6 squared plus negative 6 squared plus 2 squared. 4076. Okay, I can still factor out 4. And so norm So this is 2 rad 19. And let's look at the norm. Well, r prime at 1. R prime at 1 was 1, 2, 3. So it's R prime at 1 is 1, 2, 3. And so R prime at 1 squared plus 2 squared plus 3 squared. One plus 9 is 10 plus 4 is 14. Where's the square? And so the norm of R prime at 1 is radical 14. Okay, so I get that the curvature at 1 is equal to 2 over rad 19 times this guy cubed, which is 14 to the 3/2. And that is your answer. Well, actually, I could simplify it, but yeah, maybe I will simplify it. So it's 2 rad 19 over the square root of 14 cubed, which is just 14. I can cancel out one of the 2 to get 1/7 times the square root of 19 over 14. And that's my curvature, which is approximately 19 divided by 14. There it is. Which is approximately 0.166 4253 423535. So you should write, so 4 decimal places is 1664. And that's what you should enter into your answer box. Any questions about that? Okay. Let me do problem number 13. And so for problem 13, find the curvature of y equaling negative 5x e to the 4x. Determine the exact value of the curvature. Enter the approximate value rounded 4 decimal places when x is equal to negative 2. So let's do the curvature. And so I'll just say f of x. And so the curvature is equal to the absolute value of the second derivative. Oops. Over 1 plus f prime of x squared to the 3x. So we use that formula. And so f prime of x, it's, well, actually, maybe we should write f of x first. F of x is negative 5x e to the 4x. Yes, it is. Okay. So let's take the derivative. Use the product rule. Do the first times the second plus the first times the derivative of the second. Second derivative. Bring down the 4. Do the product rule. Do the first and the second plus the first times the derivative of the second. And so into the exact value of the curvature into the approximate value when x is negative 2. So maybe I can just plug it. Okay, so this is equal to negative 40 e to the negative 4x, minus 80 x e to the 4x. And so this is a negative 40 e to the 4x. And this would be a 1 plus 2x. Okay. Let's look at f prime squared. So first, factor out negative 5 e to the 4x. What remains is 1 plus 4x. Okay. This is 25 e to the 8x, 1 plus 4x squared. Okay, so I have here that the curvature is equal to the absolute value of this. So this would be a 40 e to the 4x over 1 plus 2x divided by the cube of this guy, divided by this guy plus 1 to 3 halves. Okay. So that's your exact formula. Let's find the value at not at the value at -2. Sorry, did I check? Value at -2. So this would be 40 e and -8, 1 minus 4. Oh, this is assuming x is greater than 0. If not, I have to put in absolute value here. Now it's correct. Okay, because x was negative. Okay, so I need an absolute value there. For some reason, I thought x was 1. Okay, so let's -2. Okay, so I have a 1 plus 25 e to the -16, and then a 1 minus 8 squared to the 3/2. So this is 3 times 40, 120 e to the -8 over horrible stuff. That would be 749 times 25, whatever that is. 49 times 25. I'm too lazy. 49 times 25. 1225. Yeah. 1 plus 1225 e to the -16 to 3/2. And let's find the approximate value. Let's plug that in. $120 e to the -8 divided by 1 plus 1225 e to the -16 to the power 3/2. Point 0.0402471926. 02. And that's what you should input into your answer box. Okay, let me do problem number 14. Any questions about this? Let me do problem number 14. At what point does the curve y equal e to the x have maximum curvature? Determine the exact value of the curvature at this point, the maximum curvature, and enter the approximate value of x rounded 4 decimal places at which the curve is maximum. Okay, well, we're going to be using basically the same formula. So the curvature okay. So yeah, but f of x is equal to e to the x, or x e to the x, e to the x. Well, that makes life really easy. So f prime is e to the x, f double prime is e to the x. So my curvature is e to the x over 1 plus e to the 2x with 3/2. Okay, so I want to optimize this. So that's my curvature. Yeah, that wouldn't simplify it that much. Okay, yeah. Okay, so let's take the, let's try to optimize this. Use the quotient rule, drew the first, drew the numerator times the denominator minus the numerator times the denominator. Multi-derivative what's inside, all divided by the denominator squared. Okay. Let's simplify that. Factor out 1 plus e to the 2x to the power 3/2. So this term is gone, so just e to the x. These cancel. This becomes e to the 3x and a 3 e to the 3x. Oh, wait, I canceled out a half of these. Okay, so here, wait 1 second. I made a mistake. I can only factor out a 1 plus e to the 2x to the 1/2. Okay, so this is to the 5/2. And this is e to the x times 1 plus e to the 2x. Minus the 2's cancel, so you get 3 e to the 3x. The 1 plus e to the 2x to the 1/2 power cancels. And so multiply e to the x inside the parentheses. Combine like terms. I have a e to the 3x minus e to the 3x is a minus 2 e to the 3x over 1 plus e to the 2x to the 5/2. Okay. And now let's, well, probably it's easier to use the second derivative test. Let's do the second derivative. By the way, what happened to the derivative? Don't know. Okay, let's take the second derivative. So derivative of the numerator times the denominator minus the numerator times the derivative of the denominator times the derivative of what's inside, all divided by the denominator squared. Cancel out lowest power. 1 plus e to the 2x to the 3 halves. So 10 minus 3 halves is 7 halves. Okay. And so this is e to the x minus 6 e to the 3x times 1 plus e to the 2x. 5 halves minus 3 halves is 1. So that's the first power. Minus. So 2's cancel. So you get a 5 e to the 2x times e to the x minus 2 e to the 3x. The 1 plus e to the 2x to the 3 halves cancel. Okay. Simplify. And so e to the x plus e to the 3x minus 6 e to the 3x minus 6 e to the 5x minus 5 e to the 3x plus 10 e to the 5x all over 1 plus e to the 2x is 7 halves. Okay. E to the x. I have here 1 minus 3 minus 6 minus 5. And so that's minus 10 of these. Minus 10 e to the 3x. I have 10 minus 6 is 4 e to the 5x's over 1 plus e to the 2x is 7 halves. Okay, so now let's try to find the, so I found the first and second derivatives. I found the first and second derivatives so I can hopefully be able to use the second derivative test. It seemed to be easier to use than the first derivative test. Okay, so let's try to determine the critical numbers. Okay, so e to the x. So let's see when this is 0 and when this does not exist. I'm looking at two different cases. Well, let's look at when it doesn't exist because it's easiest. These are a whole bunch of exponentials, so they exist everywhere. The only possible, so it's a rational expression involving e to the x. So the only, well, with the radical in there. But this is going to exist everywhere except when you divide by 0. But 1 plus e to the 2x is never 0. So we get nothing from that. So let's set the numerator to 0. E to the x minus 2e to the 2x, 3x. Okay, so I have 2 e to the 3x is equal to e to the x. And so I have that e to the negative 2x is equal to 2. Therefore, x is equal to negative 1/2 ln 2. Okay, so that's my critical number, my only critical number in this particular case. Let's check the second derivative test. Note I can use a second derivative test because the only critical numbers are those found by setting the first derivative equal to 0. Okay. Plug in. Yeah, -1/2 ln2. Okay, so here's the second derivative. So e to that number is going to be, well, 1 over the square root of 2 . Three times that is 3/2. So that's 1 over 2 rad 2. Plus 4. E to the 5/2. So that's multiplied by 5. So that's 2 squared, which is a 4. That's 1 over 4 rad 2. Multiply by e to the 2x, so multiply by 2. So it's 1 over 2. So it's 1/2. That's 7/2. Okay. So I get, there's negative. Oh, so it's a maximum. Good. Okay, so this is equal to 1 over rad 2 minus 5 over rad 2 plus 1 over rad 2 . Okay, so that becomes 3 over rad 2 . And this becomes cubed 27 over 8. Rad 3/2. So rad 2's cancel. And so you get a negative. 9 is in the bottom. 8 is in the numerator. And rad 3 is in the denominator. Okay. So the 2, 16. Sorry. No, the rad 2's cancel. I was right. The rad 2's cancel. Rad 2's cancel. Okay, so that's an 8 in the numerator. So rad 2's cancel. And 3 over rad 3 is just a rad 3. I could put the rad 3 up here. Over 27. I'll keep it in the denominator. Okay, but whatever, this is less than 0. So it's concave down. So therefore, we have a maximum. So K is maximum, curvature is maximal. And X is equal to this 1 over the square root of 2. So ln of 1 over rad 2. Okay. That's when it's maximal. And I guess we also want to find the approximate value of that. Value of x, yeah. Mhm. And so x is approximately, let me plug that into my calculator. Negative 0.34 657 35 983. So we want this to 4 decimal places. Four. It's negative. Yeah, rounding up. Okay. So it's negative. So it's a negative, and I'm rounding up. And so it's a negative 0.3465. And that's what you would input. Okay. Let me do problem number 15. Any questions about this? Oh, so this is very similar to the, of course, I'm going very slow over it with you guys, to be sure. You know, I've had also a few breaks in between. And we also did in other words, we also did a review before we started the exam, if you remember also. So yes, so it's going to be very similar questions to what I'm going over. Okay. So remember, there was an hour-and-a-half review of other stuff before we actually started the sample exam. Okay. Any other questions about this? Of course, I had a few breaks in between. Oh, wait. Okay. So let's do the following. Problem number 15. Find the curvature of x equals 3 e to the 9t cosine t, y equals 9 e to the 4 e to the 9t sine t. Determine the exact value of the curvature into the approximate value rounded to 4 decimal places when t equals -4. Okay, so let's do that. And so let's find the formula for the curvature. And so the formula for my curvature is the absolute value. I don't know. I think I'll write it this way. X, Y, minus x y. I think they actually did it with dots. They use Newton's notation in the book over the square root of x dot squared plus y dot squared. Okay, so let's figure that out. So x is 3,9. And that's a cosine. So let's take the derivative. And so I'll use the product rule. So derivative first times the second plus the first times the derivative of the second. Do the second derivative. So it's a derivative of the first nine times 27 times the second plus the first times the derivative of the second. And maybe I'll combine those. And then I'll take the derivative of this, which is derivative of the first, which is another negative 27. So this is negative 54. E to the 9t times sine t plus the first times the derivative of the second. Okay, so let's add. So this is equal to I have 243 minus 3 is 240. E to the 9t cosine t minus 54. E to the 9t cosine t. Okay. Let's pick y. I think it's the same thing, but with sine. 49 sine. Okay, let's take the derivatives. Again, use the product rule. So 36 e to 9t, derivative the first times the second, plus the first times the derivative of the second. Take the second derivative. Derivative of the first, which is 144. No, 324. The derivative of the first times the second plus the first times the derivative of the second. So I have 36 of these plus, well, derivative of the first, that gives me another 36 of these. So that's 72. Plus the first times the derivative of the second. And so I get 324 minus 4 is 320 e to the 9t sine t plus 72 e to the 9t sine t. Okay. And so let's do the numerator, I guess. Let's do x prime. Okay. So x prime. There it is. Here's my x prime. Oh, I guess I should have factored out. So maybe what I'll do is when I write it, I'll factor out some things here. Here's my x prime. What the heck? It's not x prime. Here's my x prime. Copy. That's x prime. Okay, so my x prime, let's factor out a 3 e to the 9t. What remains is 9 cosine t minus sine t. Okay, good. Now let's look at y double prime, which is right here. And let's factor out something. You could factor out like 36. Maybe 12. Not enough threes. 6, 4. A 4. I can factor out a 4. Okay, 4. E to the 9t times 80 cosine t plus. Well, can I factor out an 8? Why can't I factor out an 8, you jerk? Why can't I factor out a 16? An 8. I can factor out an 8. Okay, so I can factor out 8. I guess that's about the best I can do is factor out an 8. Okay, 40 sine t plus 9 cosine t. Okay, minus x double prime. There's an x double prime. So this factor out of 6. Okay, and so here's my x double prime. Okay, so let's factor out at least a 6. E to the 9t. What remains is 40 cosine t minus 9 sine t. Okay. And let's do y prime. Here's y prime. I can factor out of 4. Okay, so y prime. There's y prime. Okay, so it is 4 e to the 9t. And what remains is 9 sine t. Okay. So I factor out a whole bunch of stuff. Hopefully that simplifies some things at least. Okay, so I have 24 e to the 18t. Let's multiply these together. Okay. So I have 360 cosine t sine t plus 81 cosine squared t minus 40 sine squared t minus 9 cosine t sine t minus 24, 24 again, e to the 18t. And so that'll give me a 360 cosine t sine t. Okay. And then this gives me a plus 40. Well, maybe I'll do that one. Well, plus 40. So let's do this one first. Let's do this guy first because minus 81 sine squared t. And then let's do the cosine, the cosines, the other one. And so that's a, that was that. That's a cosine. Oh, that was sine squared. Oh, then the other one would be the cosine squared. So minus, so that's a plus actually, a plus 40 cosine squared t, which is good. And then minus 9 cosine t sine t. Not everything cancels. Almost everything cancels. So now, note, these cancel. These are the same, except there's minus sign. Same. These cancel. Okay. But now you get (24) e to 18t. I have 81 times cosine squared t plus sine squared t. This minus makes this minus a plus. And I have plus 40. No, that's a minus 40. Minus 40, sorry. Minus 40 sine squared t plus cosine squared t. Plus, of course, sine squared t plus cosine squared t is 1. So you get a 41. So this is just equal to 24 times 41. I'm going to be lazy. Just 20 frames. 984. Okay, good. So that's my numerator. Of course, I took the absolute value of it, but I really don't care about the absolute value because this is a positive quantity. Okay, so that gave me my numerator. Here's my numerator. Now I just have to figure out the denominator. Let's figure out my denominator. I need some more space here. X. Okay, so let's look. So again, here's my X dot O, which is this. Here's my X dot, which I've already factored. My X dot, oops. Copy, paste. There it is. So that's my X dot squared. And here's my Y dot that I've already factored nicely. Squared. I guess I'll just leave it on next line. It's too big to get on one line, I guess. Okay. No, there's nothing there. Okay, so this is equal to 9 e to the 18t. Square that, so that's 81 cosine squared t minus 18 cosine t sine t plus sine squared t plus 4 e to the 18t times 81. This is not going to be the same. 81 sine squared t plus 18. These won't be the same either. Because that's a 4 and that's a 3. Okay. Plus 18 cosine t sine t plus cosine squared t. Okay, so this is equal to e to the 18t. First, I guess let's let's deal with this guy here. Okay, so it's 81 of these. And I have 9 of these, which is more. And so I have a 5 more of the cosine squared than the sine squared, but the 4 cosine squared plus the sine squared gives me just 4. I'm going to write it that way, I guess. Okay, plus 9 of these minus 5 of them gives you a minus 5. 9 of these minus 8, 4 of them minus 9 of them gives you negative 5. So minus 5 of these times 18. And 9 of these plus 4 of them give you 5 more. So 5 sine squared. Oh, 5 sine squared t plus 4, which is 82 of those then. Okay, so I get e to the 18t, 82 of the 5 cosine squared t plus 4, and 90 of the cosine t sine t's. That's about as simple as you can write it. You can multiply the 82 inside the parentheses, but who cares? Okay, so now, lastly, we have numerator. Oh, and that's the square root of that guy. Oh, actually, let's just see if I could factor this. Let's see if I can factor it out. So let me multiply this out just one. Let me go just 1 second further, just in case. And so I have here 82 times 5, which is 420. Yeah. Way I can factor it. It's going to factor. Plus 4 times 82. 328 minus 90 cosine t sine t. Yeah, there's no way adding and subtracting some cosine squares and sine squares from this guy will make that into a perfect square. Okay, so I have here, therefore, the square root of x prime squared plus y prime squared is e to the 9t radical this stuff. 410 cosine squared t minus 90 sine t plus 328. Okay, so therefore, we have that. Ooh. This is equal to numerator, which wasn't too bad. Oh, 984. E to the 18t over, oops, e to the 9t times radical stuff. Okay, so you can cancel those out. We get 984 e to the 9t over rad 410 cosine squared t minus 90 cosine t sine t plus 328. Okay. And you want to figure this, I think, when t is something. T is -4. Okay. Here's your answer. Let's plug that into my calculator. Okay. Oops. Calculator. There it is. Okay, so, and I can't do it in radians, so 984 times e to the -36 divided by square root of 410 cosine of pi over 180 obviously that could have been simplified squared. Okay, cosine squared of that. To make it into radians, no. I have radians. So I have to multiply. I multiplied it wrong. 180 over pi. Huh. Oh, that's all. That's nice. 984 e to -36 divided by, divided by the square root of 410 times cosine one d square that and cosine -4 times 180 over pi times sine -4 times 180 over pi plus 328 is tiny, is 0. Okay, is 9.752701041 times 10 to the negative 15, which the 4 decimal places is 0. So your answer is 0. The curvature in this case is 0. Any questions about that? Okay, let me check. Oh, there is something. Yes, the recording will be uploaded to Zoom today. Okay. Any other questions about anything? Okay. Let me do problem number 16. Find the unit tangent, unit normal vectors t and n, and find the curvature. Enter the approximate value of the curvature, rounded 4 decimal places when t is equal to 1. Okay. Oh, r is equal to the vector with components 9t comma 5 cosine t comma 4 sine t. Okay, good. So let's find the unit tangent vector, the normal vectors, and the curvature. And let's see the formula to use. This is just r. Okay, so I'll just write it this way. And I'm going to be lazy. And the curvature is t prime over the norm of r prime. Okay. So let's figure out each of these. So first, figure out r prime. Well, r is 95 cosine and 4 sine. So r prime is 9 negative 5 sine t 4 cosine t. Let's figure the square of r prime. So I'm just leaving off the variables. Okay, so this is equal to 9 squared plus negative 5 sine squared, sine t. Come on. Squared plus 4 cosine t squared. So I have here 81 plus 25 sine squared t plus 16 sine squared t, which is equal to, you can do 16 of these, so that's 9. 81 plus 9 sine squared t plus 16. So that's 97 plus 9 sine squared t. And so the norm of r prime is radical at 9 sine squared t plus 97. Okay. So now let's figure out t. And so t is just equal to, well, 1 over this, 9 sine squared t plus 97 to negative 1/2 times r prime, which was 9 negative 5 . Oh, it's a sine, and the other one's cosine. So 5, 4. Yeah, okay. I better check that was the prime I'm looking at. Okay. And that is correct. Okay. So that's the unit tangent vector. Okay, let's find the normal vector. So let's first find t prime. So let's take the derivative of the first. Drop down to negative 1/2. Subtract 1 from the exponent. Times the derivative of what's inside. So it's going to give you a 2, which will cancel. And so you have a minus 9 sine t cosine t. Times the second. Plus the first. Times the derivative of the second. Okay. Derivative of cosine is minus sign. Okay, and so let me factor out a 9 sine squared t plus 97 to the negative 1/2. Okay. To negative 3/2. Okay. And so this is equal to, multiply this, 9 negative 9, the negative 9 sine t cosine t inside the vector. So it's a negative 81 sine t cosine t, 45 sine squared cosine, and negative 36 sine cosine squared. Okay, plus. Okay, so now I factored this out, so I still have another one. I have to multiply this inside the parentheses. And so it's a 9 sine squared t plus 97, a minus 45 sine squared t cosine t, and a minus for 85 cosine t. And I have a minus 36. Let me just check. Okay, so now here's a quick question. How did I get the derivative of 9 equaling 1? Okay, so derivative of 9 is 0.
It's all right.
Derivative of 9 is 0.
And now I can't breathe or any something. It was horrible. I don't want to watch it. Let them do something else.
Okay, and I'm taking the derivative of cosine, which is minus sine. Okay, so that still is a minus. Okay, so that's a minus.
Did you come in here?
36 sine squared t sine cubed t
Are you coming now?
minus 36 sine cubed t
Could you please hurt me?
minus
Could you please? One time, can you make me read one?
minus, sorry.
This is so gives you what it is. Go ahead.
Okay, minus 388. Sorry, minus 388 sine t. Okay. And so I get 9 sine squared t plus 97 to the negative 3 halves, negative 81 sine t cosine t. Those cancel. Minus 45, 485 cosine t. And I get a minus 36 sine t times, factor out the cosine squared t plus sine squared t. And then I get a minus 388 sine t. Okay, so this is equal to 9 sine squared t plus 97 to negative 3 halves, minus 81 sine t cosine t, minus 485 cosine t. I have here cosine squared t plus sine squared t is 1. So this is just minus 36t minus another 388t. And so I can just add those together, the 388 and the 36. Get a negative 424. Negative 424 sine t. Okay, good. And so now let's find the norm. So let's square that.
Nothing's in there. Nothing.
So I have here 81, and let's just square that. So that's 65, 61, sine squared, cosine squared t. And let's take the 485 and let's square that. That's going to be pretty big also. And so that's 235,225 cosine squared t plus, I'll just write it here, plus the 424 squared, which is 179. $776 sine squared t. And so I have that the norm of t prime squared is 9 sine squared t plus 97 to negative 3. And so that's 650, 65, 61 sine squared t cosine squared t. And let's do the 235, 225. Subtract from that the 179, 776. So we have, I have additional 55,449 of the cosine squares plus $179,776, where I combine the sine squares and cosine squares. Okay, and so I have that the norm of t prime is 9 sine squared t plus 97 and negative 3/2 times the square root of what remained, the 6561 sine squared t cosine squared t plus 55,449 cosine squared t plus 179,776. Okay, so I have that the normal is equal to divide by that. So this is 9 sine squared t plus 97 to the 3/2 over this guy, 6561 sine squared cosine squared plus 55,449 cosine squared t plus 179,776 all times. Okay, t prime, which is this guy. Oh, okay, so let me write this guy here. Okay, times this guy. So if you multiply by this guy, then that becomes to the first power. Okay, so that's just the first power. And then what remains is 9 minus 5 sine t or cosine t. And that is your normal vector. And the curvature will equal, oops, that's missing, will equal this guy. And let's skip one line. Times the square root. 65, 61, sine squared t, cosine squared t, 55, 449, cosine squared t, plus 179776. Okay, divided by the norm of r prime, divided by this guy, the square root. Divided by the square root, which means this just becomes another square root. So I should write it here at the bottom and just add another square root. So that makes it quantity squared. And that is my curvature. And then they said to like evaluate at 1 or something. Yeah, evaluate at 1. I was guessing. Okay, so let's plug in 1. Oh, it's sines and cosine. It's not nice numbers because they're sines and cosines. Okay, and we'll plug this into our calculator. Okay, so let's plug this into our calculator. Unfortunately, it doesn't give me radians, so I have to do everything in degrees. So it's the square root of 6561 sine of 180 over pi and then you're going to square it. Cosine 180 over pi squared plus 55449 cosine 180 over pi. And you're going to square it plus 179776 And then you're going to divide by 9 sine 180 divided by pi squared. No, yeah, squared at 97 squared. It is 0.041569358. It is approximately 0.0416. And that's what you should input into your answer sheet. Okay, any questions about that? Sorry, I was interrupted a few times during that calculation. Okay. Let's do problem number 17. Find the equations of the normal plane, the oscillating plane at the curve at the given point into the value of z on the normal plane when x is 5 rounded 4 decimal places. Okay, so I have to find the normal plane. Oh, and x here is equal to the sine of 2x, y is equal to negative cosine of 2x, z is equal to 4t, and we're at the point 0, 1, 2 pi. Okay, so I'm going to need to find the tangent vector, the unit tangent vector the normal vector, the binomial vector, and then the normal and oscillating planes. Okay, so I need to find, and again, I'll just sort of be lazy. I'll just write it without the variable. And so the unit, why do I have a derivative here? Don't know. The unit tangent vector is r prime over the normal of r prime. Normal vector is t prime over the norm of t prime. Binormal is t cross n. The normal plane is the one that's the NB plane. It's a plane containing the vectors n and b, and the oscillating plane is the one containing the vectors n and t. Okay, so let's do this. And so I have here R is equal to sine cosine. Okay, so R is equal to sine 2t minus cosine 2t 4t. R prime is 2 sine 2t. And I have a 2 sine 2t, and I have a 4. Okay, so let's find the length of this. So that becomes a 4 cosine squared 2t plus 4 sine squared 2t plus 16. That becomes sine squared plus cosine squared 2t plus sine squared 2t is 1. So that's 4 plus 16, which is 20. And so the norm of R prime is equal to 2 rad 5.
No water in here? Is there?
So I have here that the unit tangent vector is therefore equal to, so divide everything by 2 rad 5. The 2's are nice. So maybe I'll write this as 1 over rad 5 cosine 2t sine 2t 2. Okay. And that is my tangent vector, unit tangent vector. Let's take the derivative. So it's a minus 2 sine 2t plus 2 cosine 2t 0. Let's find the length of this squared. And so this is 1/5 4 sine squared 2t plus 4 cosine squared 2t, which is equal to 4/5. And so the norm of t prime is just 2 over rad 5. And so the normal vector is, I'm going to divide by that. And so the rad 5's cancel. So I'm dividing everything by 2. So just divide by 2. So minus sine 2t cosine 2t 0. That is my normal. Let's find the binormal. Which is the cross product of t 1 over rad 5 cosine sine 2. I'm going to cross it with minus sine t 2t cosine 2t 0. And so I get 1 over rad 5, 0 minus 2 cosine 2t, minus 2 minus 0, so minus 2 sine 2t. And lastly, cosine squared 2t plus sine squared 2t, which is 1. And that is my binormal. Okay, so now let's find a normal plane. And I want the normal plane through 0, 1, 2 pi. Okay, I can choose, oh, okay, so now it's through N and B, so it's T. So it's something parallel to T. So my normal vector, so normal to this normal plane. So my normal is going to be something parallel to T. And so I'll pick for my normal cosine 2t, sine 2t, and 2. So I'll pick for my normal. Oh, I already forgot. Cosine sine. Okay. Okay, and so the equation normal to this through the point is going to be oh, and I guess you want at this point. So let's choose it. So notice that t is equal to, oh, this is, so 4, oops, 4t is equal to 2 pi. So t is equal to pi over 2. Okay, so notice sine of pi is 0, cosine of pi is -1, so negative that gives you +1. So t here is pi over 2. So let's do this at pi over 2. So for my normal, I'll do the cosine of pi, sine of pi. And so the equation will be -1 x minus 0 plus 0
When is Gubba gonna come?
y minus 1 plus 2 z minus 2 pi equals 0. And so that says that 2z minus x is equal to 4 pi. And that's the equation of my normal plane. Let's determine the equation for my oscillating plane. Okay, so Let the normal to this plane equal. So the normal to this plane will be parallel. This oscillating plane includes both the normal, the tangent, unit tangent vector, the normal vector. So the binomial vector is normal to this. So let's pick a something parallel to the normal, to the binomial vector. Okay, so here's the binomial vector. So I'll pick something looking like this. So -2 sine 2 pi, sine 2 pi, and a 1. They're both minuses. Okay, so minus and a minus, -2 and a -2. Okay, and let's do this at pi over 2. Okay, so for my normal, I'm going to pick 2, 0, 1. Okay, so my oscillating plane will be 2 times x minus 0 plus 0 times y minus 1 plus 1 times z minus pi over 2 minus 2 pi. So I have 2x plus z equals 2 pi. That is the equation of my oscillating plane. They wanted to do something. Find the normal plane. So I'm looking at the normal plane when x is 5. Normal when x is 5. So what's the normal plane? 2z minus x. So 2z minus x is equal to 4 pi. Okay, and I let x equal 5. And so z is equal to 4 pi plus 5 over 2. And so z is approximately, so let's figure out what z is. There it is, finally. So z is 4 pi plus 5 divided by 2. .7 831 85 3072. Okay, and so z is approximately 4 decimal places 8.7832, and that's what you should enter into your text box. Okay, any questions about that? Okay. Problem number 18. A ball is thrown eastward in the air from the origin in the direction of the positive x-axis. The initial velocity, is, well, here it is. So 50 I plus 80K with speed measured in feet per second. The spin of the ball results in a southward acceleration of 4 feet per second. So the acceleration is A is equal to a negative 4J minus 32K. Where does the ball land and with what speed? Enter the speed in feet per second rounded 4 decimal places. Okay, so let me sort of try to draw this. Let's do it this way then. This is the K direction, J direction, and the I direction. Okay, so he is doing it like almost straight up. So initially, so your initial velocity is 50 I plus 80 K. And we have some sort of spin on this ball. And so the spin on this ball gives us some sort of path where my acceleration is doing something. So my acceleration is negative 4J plus, minus 32K. And we're doing everything in feet per second. Okay, so I have the acceleration is negative 4J minus 32K. So let's integrate this. So I have the integral of V prime is the integral of negative 4J minus 32K. And so I have that the velocity is negative 4 TJ minus 32 TK plus some constant vector. Well, let's plug in T equals 0. So plugging in T equals 0, well, these guys are 0. So I have 50 I plus 80K is equal to C. Okay, so my vector, constant vector is equal to that. I don't think I need to. Okay, so I have the velocity is equal to a 50I plus 80, the minus 4 TJ plus 80 minus 32T K. Okay, so that's your velocity. Next, let's figure out the, I can figure out the speed now. Oh, and so let's figure out where it lands. Okay, so let's integrate this. So let's integrate this. So the position is 50t I minus 2t squared j plus 80t minus 16t squared k plus some constant vector. I'm assuming that at 0, we're at 0. And so plugging in 0 here. All of these at 0, when t is 0 is 0. So my constant vector is 0. Okay, so here's my position vector. So that's my position vector. Now we want to figure out, where does the ball land? So the ball lands when k is 0, when it's no longer above the ground. So I want to figure out, well, when the, I shouldn't say when k is, when the component in the k direction, the component of the position vector in the k direction is 0. That's a much more, that was the actual correct statement. So I want to set this equal to 0. And that will tell me, that will tell me when the ball lands. So the ball will land when this is 0. So let me factor out 16t. So setting each factor to 0. I get t is equal to 5, or t is equal to 0. But t equaling 0 just says that, this is launching from the origin, and so that's not where it lands, that's where it starts. So that's not where it's ending, that's where it's starting. Okay, so it's landing, or wherever it's hitting the ground, it's landing on the ground when t is 5. Okay, so let's figure out its position. So where does it land? It's 50. Minus 2. Plus 80. Minus 16 times 5 squared. Okay, so it lands at 250 I minus 50 J, and this last term is 0. 400 minus 400 is 0. Okay, so that's where it lands. So it's gone 250 feet in the x direction, or in the I direction, and it's gone backwards 50 feet in the j direction. So it's, more or less, well, I guess, looking over here. So if I drew it, it's really landing over here. So it starts here and it lands somewhere, in the positive this direction, but a little bit in the negative that direction. So it's somewhere over there that's actually landing. So I guess I exaggerated with what it was doing, but it actually goes and curls out and lands here with, and this is my acceleration. Maybe I'll do it there. So it sort of lands like that, somewhere in back of you, or well, sort of. Okay. It has this little twist to it. Okay, and that's where does the ball land? That's where, and what speed? So now I have to figure out the speed. Great. Oh, I see. I just sort of, I guess I'll just move these guys up. Accidentally cut. Put the extra page in the wrong place. Okay, so now I guess we want to figure out the speed that it lands at. The speed when it hits ground. Let's figure that out. Okay, so let's look at R prime at 5. Oh, or V. You actually called it V. Okay, so let's look at V. Here's V. And let's plug in 5. And so V is equal to 50 minus 4 times 5, 20. No, maybe I'll do that. Plus 4 times 5J plus 80 minus 32 times 5. Okay. So 50I minus 20J minus 80. Okay. And so let's find the speed. Let me add those all up. And 50 squared. 50 squared plus 20 squared plus 80 squared is 9,300. Okay, so my speed when it hits the ground, that looks like an S. That's not good. Is 10. We're at 93 feet per second. And so it is approximately, don't know, it is approximately 96. 4, 3, 6, 5, 7, 6, 0, 9, 9. 96.4365 feet per second. And that's what you should enter into your answer box. Any questions about that? Okay. Let's do problem number 19. And so, find the tangential and normal components of the acceleration vector. Enter the approximate value of the normal component of the acceleration vector rounded 4 decimal places. So R is cosine Ti plus sine Tj plus Tk, and I'm assuming here T is greater than 0. Okay, so let's determine the normal and tangential components of acceleration.
Did he say he was gonna come here?
And so
What?
I have here that the tangential component of acceleration is just the derivative of the speed, and the normal component of acceleration is just the norm of R prime cross R double prime divided by the norm of R prime. Okay, so let's do that. I'll let you put these little vectors here. Okay. So I have here that R is equal to cosine sine T. Okay, so let's take the first and second derivatives. Minus sine T cosine T1 minus cosine T minus sine T 0. Okay, and let's take the cross product. Okay, 0 plus 1 plus sine T minus cosine T sine squared plus cosine squared T. So sine squared T plus cosine squared T is 1. Let's find the norm of this. So sine squared T plus cosine squared T plus 1, which is equal to 2. And so the norm is just right at 2. Let's find the speed. So it's cosine squared, no, sine squared plus sine squared plus cosine squared plus 1. Oh, it's the same thing. So sine squared plus cosine squared plus cosine squared plus 1. It is 2. And so my speed is equal to the square root of 2. Okay. So the derivative is 0. So everything is in the so they, okay, so so let's look. So the tangential component of acceleration is 0. Let's find the normal component of acceleration. So it is this divided by this divided by that. Okay, so it is the square root of 2 divided by the square root of 2, which is 1. So the normal component of acceleration is 1. It's only going in the normal direction. So it's only going in the normal direction. So that's why it is. And it says, find the normal component of acceleration, rounded to 4 decimal places. Well, that's what it is. It's 1. Any questions about that? Okay. Problem 20. Show that every vector, that every point on the curve, the vector with component E, T, cosine T, comma ET, sine T, comma ET, the angle between the unit tangent vector and the z-axis is the same. Then show that the same result holds true for the unit normal vector and the binomial vector. Okay, so let's do that. So I have to find the unit tangent vector, normal vector, and the binomial vector. And so I have that. This is just R prime over the norm of R prime, suppressing the T. I have here that, ouch, N is equal to T prime over the norm of T prime. And B is equal to T cross N. Okay, so let's do this. So R is e to the T let me factor out the e to the T. So it's e to the T, cosine T sine T 1. Okay, so let's find the derivative. So derivative first times second plus first times the derivative of the second add these. So it's cosine T minus sine T and sine T, well, cosine T plus sine T and 1. Okay. So now let's find the length, the square of the length. Let's use e to the 2t. So let's square this. So it's the cosine squared t minus 2 cosine t sine t plus sine squared t. Let's do the second one. And so that's going to be plus cosine squared t plus 2 cosine t sine t plus the square of the last one, sine squared t plus 1 squared, which is 1. So this is equal to, cancel, oops, cancel, cancel. Cosine squared plus sine squared is 1. Sine squared t plus cosine squared t is 1. So 1 plus 1 plus 1 is 3. So it's equal to 3 e to the 2t. Therefore, this is just rad. It's just e to the t rad 3. Okay. And so I have that the unit tangent vector is just this guy divided by that. So I'm going to divide each of these by rad 3. Okay, so 1 over rad 3 cosine t minus sine t, cosine t plus sine t, 1. Okay, so that is what t is equal to, the unit tangent vector. So now, well, let's see, should I do all of them? Okay, so let me show you the next, that the angle between this and the z-axis is the same. So the angle between t and z-axis is the same for all t. So let's try to show that. Okay, well, what is something that is parallel to the z-axis? Well, k. And so I have that it's parallel to the z-axis. Okay, so to show that, well, let's find the angle. How do I find an angle? And so recall that A dot B is norm A, norm B, cosine theta. And that will give me the angle in between these two vectors, A and B. Okay, so, and usually we make the following restrictions. Okay, so we want to show that, well, if I take t dot k, well, let's see what t dot k is. So t dot k is, well, 0, 0, so 0 plus 0 plus 1 over rad 3. Because k, obviously, the I component of k is 0, the j component of k is 0. So you just have a 1 in the k position. So this is equal to 1 over rad 3. Okay, let's look at the norm of t. The norm of t, didn't we already do that? Oh, I didn't do the norm of t yet. It's a unit vector. The norm of t is 1. It's a unit vector. So I know the norm is 1. So this is 1.
Wait a minute.
The norm of k is also 1. It's a unit vector.
When do you think she's gonna come?
And so we have that 1 over rad 3 is equal to 1 times 1 times cosine theta. Therefore, theta is equal to arc cosine of 1 over rad 3. And this does not depend on t. It doesn't depend on t at all. It's a constant. And so the angle is a constant. So it doesn't depend here on t at all. There are no t's anywhere. The t's are disappeared. Okay, so that says that the angle between t and the z-axis is the same for all t. All t. Okay, so now let's look at the normal vector. Let's look at t prime. Here's t. Let's look at t prime. And so it is 1 over rad 3. Derivative of that is minus cosine, that's minus sine, minus cosine t. Derivative is minus sine plus cosine t. Derivative is 0. Let's look at the norm of t prime. Square 1/3. Square this out, and so it is sine squared minus a minus, make that a plus 2 sine t cosine t plus cosine squared t. Let's square this one, and so it's a sine squared t minus 2 sine t cosine t plus cosine squared t. Okay. These cancel. And I have here cosine sine squared t plus cosine squared t is 1. Sine squared t plus cosine squared t is another 1. So this is equal to 2/3. Oops. Which implies that the norm here is radical 2/3. Okay. And so I have here that n is equal to t divided by that. So it's the same thing. It's just that I'm going to be divided by 1 over rad 2. So 1 over rad 2 minus sine t minus cosine t minus sine t plus cosine t 0. Okay. So now let's do the same thing we did before. Let's show that the angle between n and the z-axis is the same, all t. Okay. So again, let's look at, well, the norm of n is 1. The norm of k is 1. These are all unit vectors. Let's look at n dot k. There'll be a 0 plus the whatever the k component is, which is 0. So this guy is 0 also. That's 0. So this is 0. Okay, so we have that since n dot k is equal to norm n, norm k, cosine theta for theta between 0 and pi. We have 0 equals 1 sine theta. So cosine theta is 1. So the cosine of theta is 0. Okay, so that just says that, well, if it's 0, that means that theta is pi over 2. But pi over 2 is a constant. And so, again, this is a constant, so it's the same. So theta is a constant. And that's what we wanted to show. Last, B. Is equal to T. T. There's T. Oh, that's not supposed to be there. That was, get rid of that. That was there to help me with something else. Cut. But that's okay. I wanted it here anyway. So it's equal to this. So it is, actually, I'll just copy it. I'll just do that. Cross n. And here's n. I'll just copy that and put it down here. There. And so this is equal to 1 over rad 6 times 0 minus, and so this is sine t minus cosine t. Next, minus that, minus 0, so minus that. So minus sine t minus cosine t. And then lastly, oh, good grief. So this, let's multiply these together. Okay, so this is the same. So this is, I can't do it in my head now. This is cosine t minus sine t squared minus, go the other way. Minus and minus is a plus. Cosine t plus sine t squared. Okay. So this is equal to 1 over rad 6. Sine t minus cosine t minus sine t minus cosine t And this becomes cosine squared t minus 2 cosine t sine t plus sine squared t plus cosine squared t plus 2 cosine t sine t plus sine squared t. Okay, so this is equal to 1 over rad 6. These are the same. Sine t minus cosine t minus sine t minus cosine t, and cancel, cancel. Cosine squared t plus sine squared t is 1. Cosine squared t plus sine squared t is 1. 1 plus 1 is 2. Okay, so now we're doing the binormal. So we have here that, from the formula for the dot product, b dot k is equal to norm of b times norm of k times cosine theta. And so let's do b dot k and so b, this is b dot k is 0 plus 0 plus 2 over rad 6. So 2 over rad 6. Notice no t's. Okay, norm of b is a vector is 1. Norm of k is 1. So I have 2 over rad 6 is equal to 1, 1 cosine theta. And so I have that cosine theta, that theta is equal to the arc cosine of 2 over rad 6. But this is a constant. And so this implies that theta is constant. And that is what we wanted to show. Oh, and we're done. So I didn't need that one. And so we wanted to show that it was a constant. And it is constant. It doesn't depend on, on theta. On t, doesn't depend. Theta does not depend on t. Okay, so that